in this problem, we have to think backwards about our properties like intercepts and asymptotes. In this case, we're not starting with a rational function and trying to identify these characteristics. Instead, we're starting with the characteristics we would like to have and then finding an equation for a function that does that. So let's just check off these things as we go. If I want a rational function to have vertical asymptotes at x equals 3 and x equals minus 1, then I need the denominator of my rational function to be 0 when x is either of those two numbers. So starting off with this product, x minus 3 times x plus 1, the denominator, will ensure that when x is 3, I get a 0, or when x is minus 1, I get a 0. So this denominator will guarantee that when x is 3 and when x is negative 1, that I'll have 0 in the denominator, and then that will cause me to have a vertical asymptote in my function. Similarly, to have x-intercepts means that we need the numerator of our rational function to be 0 at these values of x. So again, I can do this one factor at a time by having these two factors, x plus 3 times x minus 5. I can see that when x is negative 3, this factor will be 0, making the whole numerator 0, making the whole function equal to 0. And also, when x is 5, it'll make x minus 5 equal to 0, making the whole numerator 0, making the whole function equal to 0. So this function will definitely have the properties that I have in number 1 and number 2. It'll have the right vertical asymptotes and the right x-intercepts. And so to show you that, I made a picture of what I've done so far. I can get it out from behind here. I have it hiding back here. So here's a picture drawn by Desmos of the function that's sitting in front of you right now. And we can see that the x-intercepts are at negative 3, 0, and 5, 0. So that was one of our goals. And you can see the asymptotes, more or less. We can see the that there's asymptotic behavior right through here. If I can highlight that one line well enough. My graph is approaching that blue line over here going up and over here going down. And so this blue line will be a vertical asymptote, and that's the vertical asymptote at x equal negative 1. And over here, halfway between 2 and 4, I can see that I have another vertical asymptote. This is a vertical line where the graph is getting close to it from the left side up here and from the right side down here. So this will be my vertical asymptote at x equals 3, and this will be my vertical asymptote at x equal negative 1. Now, the one thing that's not right about this graph is that it does not have the right horizontal asymptote. If I kind of draw a sketch in, I can see my horizontal asymptote is right along here. My graph looks like it's going to hug that green line, and that green line has equation y equals 1. You can see it right here. That is consistent with what we learned about horizontal asymptotes. In this function, the function that I've drawn here, I can see that the highest degree term in the numerator is going to be x squared, and the highest degree term in the denominator is going to be x squared. So out at the extremes, this function is going to behave just like x squared over x squared, and of course x squared over x squared is 1. So that's why we're seeing it getting closer to y equals 1. So to make the horizontal asymptote be something else, I really just need to I'm just going to put the number 8 out here. And so what that'll do is now the numerator's lead term is going to be x times 8. So now I'll have 8x squared as the leading term of the numerator. And there's still just x squared as the leading term of the denominator. So So this expression will look more and more like 8x squared over x squared, which is just 8, as we get out to the extremes. So putting the 8 there is going to multiply the y-coordinate that we were approaching by 8 and send it way, way up there. And you can use Desmos to check that really does do the trick and it doesn't lose any of these other properties that we have decided on.